Math prodigies, welcome back to another linear equations video. This one is on parallel lines and why we care about them. Take a look. Alright, so when we talk about parallel lines, you probably know by now that we're talking about two lines that run side by side that will never touch. Now the example most of us have learned is that train tracks example. If you picture train tracks, they run beside each other, but they never touch. Now in our math class, what we care about parallel lines is that they have the exact same slope. And this makes sense if you think of the slope or the steepness of a line. Two lines that run side by side are going to have the exact same steepness, the exact same slope. And two lines that have the exact same slope are going to run through the graph at the exact same angle or steepness, and that means that they're parallel. Now you have to remember that slope is the a value in y equals ax plus b. Why is that important? Well, if we're asked to prove, or we have to prove, that two lines are parallel or they're not, what we have to do is look at the slope. So in y equals ax plus b, that was the a value. The other way to prove that two lines are parallel is to use the slope formula, which we also remember. And whichever way you're going about getting the slope, well, once you get an answer, if the two are the same, then yes, you have parallel lines. And if you have different answers for slope, then you don't have parallel lines. So does it get any tougher about parallel lines in this class? Well, kind of. Now, if you think of any two lines that are parallel, you know that they'll never cross. All other pairs of lines in the world will cross at some point. So usually two lines, unless they're parallel, are going to cross once and only once. Straight lines can never cross twice, right? They would have to turn back and then re-meet somehow, which, although romantic, is not possible with straight lines. They are straight and they stay straight forever. Now parallel lines are different because they'll never cross. They'll run side by side, but they'll never meet or touch. But now picture two lines that are parallel, but that also have the same y-intercept. So we can't really say that these two lines never cross, and we can't say they cross once and only once. What we say here is that these two lines cross at infinite points along the graph. So if you think of the point where two lines cross as just the point where they meet, well, these two lines are meeting at every step of the way. Anywhere you go on the Cartesian plane, these two lines are together. Now this concept is important for you to understand because it's pretty common that on an exam they're going to ask you about two lines. They're going to give you two equations and they're going to ask you, do these two lines cross once, twice, never, or do they cross at infinite points on the graph? Now you got to consider the two equations to be able to answer the question. And to answer this question, you could eliminate the answer twice right away. No two straight lines are ever going to cross twice. But most lines do cross once and only once. Now the other two options, never or at infinite points do they cross, those have to do with parallel lines. Now two lines that never touch, that never cross, we call those parallel and distinct. Distinct meaning that they are different from each other and will never cross. The other type of line, this last option here where they cross at infinite points or they touch at infinite points on the graph, those we call parallel and coincident. Coincident lines are parallel, yes, but they also have the same y-intercept, meaning they touch at infinite points on the graph. Now the only other thing they could ask possibly is like a yes or no type question. They'll give you a couple of equations or some information, maybe two sets of coordinates, and they'll ask you, hey, are these two lines parallel or not? All you're going to have to do is prove that their slopes are either the exact same, making them parallel, or different, meaning nope, they're not parallel. So that's pretty much it for parallel lines. Try and remember those few key points. And they were, parallel lines have the exact same slope. Parallel lines never touch, unless, of course, they have the same y-intercept, in which case they always touch. And specifically, in case you see those words on a final exam, parallel and distinct means yes, they're parallel, same slope, but a different y-intercept, meaning they don't cross. And then parallel and coincident, meaning parallel and the same y-intercept. Two lines, one right on top of the other. So that's pretty much it. Watch the examples on questions that might come up on parallel lines.
Hey guys, we're going to take a look at parallel lines now, and you saw from the video that one of the questions that comes up is they like to ask us, particularly in the multiple choice section of exams, how many times lines might cross. They don't word it that way. They say, how many times do the lines represented by the following two equations touch or intersect each other? Sometimes they'll say, how many solutions are in the following system of equations. At the end of the day, though, before we figure out or talk about the interpretation of the possible answers, I'm going to tell you without thinking, the first thing we're going to do is we are going to isolate y in both of these equations. We can't answer anything about the nature of parallel lines until we have the equations in y is equal to ax plus b form. So we're going to go ahead and do that right now. Equation number 1, in order to isolate that y, you can see that the 20x and the negative 16 are already on the right hand side of the equation. The only thing we need to get rid of is that 4 being multiplied to our y, and we're going to do that by doing division. So straight up division on all the terms, and we're going to be left with y is equal to 5x minus 4. So we'll talk about what that could mean relative to this line once we've isolated that line. So same deal, we're going to isolate. Now this one has some extra steps because everything is on the left hand side, and I've got to isolate that y with the 36 over here, with that 45x, and then with the coefficient of the y, the 9. So I'm going to start off by adding 36 to both sides, and that'll leave me with 9y minus 45x is equal to positive 36. And then I'm going to add 45x to both sides in order to get rid of that term. So that's going to leave me with 9y is equal to 45x plus 36. And now, of course, I'll do the division of the 9, and that's going to leave me with y is equal to 45 divided by 9. You guessed it, 5x plus 36 divided by 9, you know, is 4. So now that we've got these two isolated, we can actually start to think about what the question means. And so we want to know how many times these lines intersect. Well, let's come down and do our interpretation here. First thing we know already is that lines can't cross twice. That's impossible. If you just take a really quick look at a graph, I mean, no matter where two lines go, because they're straight, they're only ever going to cross in one location, right? So if that's one line over here and that's another line over here, that's the only place that's going to happen. It's not like the line is going to come suddenly and twist and cross in a second location. So we can get rid of that guy. Now, whether they cross once, never, or at infinite points really depends on one key feature to start, and that's the slope. So we're going to start off by analyzing the slope. We know that the slope of this line here is 5. Because we've isolated, we've put it into y equals ax plus b. We have the coefficient of that x is a 5. And over here, we also have a slope of 5. Now, what that means is that these two lines are parallel. And the fact that they're parallel means one of two basic things. It's possible that those two lines, if you think about these two pencils for a second, that those two lines are like these two pencils. They're parallel, like train tracks. They're never going to touch each other because they have the same slope. It's very possible that these lines never, never, never touch. So C is looking mighty tempting right now. We know that A is impossible. It's impossible for these parallel lines to touch one time because the second I change the slope is when that's going to happen, where they have an intersection. I don't have that situation. So once is gone. But I have to pay attention to D for a second because sometimes this pops up. There are two types of parallel lines, right? One set of parallel lines are like my pencils before, right? One like this, and they're parallel, they never touch. And in the other instance, you can have parallel lines where there's one, but the second one is kind of laid down right over top of it. In other words, the same equation. And so we have to ask ourselves, okay, well, what's going on here? Well, here's the key. I have the same slope, so it's either this or this. Now I'm going to look at the b. And in this one, you can see that the b is a negative 4, whereas over here the b is a positive 4. So these are not the same equation. And what that means is they have different y-intercepts. And that means it's got to look like this, right? This line will cross at positive 4, whereas this line crosses at negative 4. They're parallel, they have the same slope, but they have different b's, which means they never touch. if you've got same A with a different B, then you are dealing with parallel lines that never touch. If you had same A, same B, well, then you'd be dealing with lines that overlay each other and would have infinite solutions. But that's not the case because we can see our B's are different. We're dealing with same A, different B. You can write that down on a memory aid. If you've got the same A with different B's, they never touch. And if you've got the same A with the same B, they always touch. If you have different A's, they touch once, never twice. Hey guys, we're looking at another parallel lines question. This one though is in a slightly different context. Here we've got Lauren claims that the following four-sided shape is a parallelogram, and you can see the keyword parallel buried in that shape, and we want to know if she's correct, and then you've got to justify your answer, which is really just a fancy way of saying explain your thinking. Well, we need to remember that in parallelograms, opposite sides must be parallel in order for it to be a parallelogram. And what that means is, if we think about these two sides right here, AB, right, has to be parallel to CD, this side and this side, and at the same time, AD AD would have to be parallel to BC. So I'm going to check to see if those sides are in fact parallel, and if it turns out that this is parallel to this and that this is parallel to this, then we know that this is a parallelogram. We can say yes. If it turns out that these two are not parallel, or that these two are not parallel, then we could say it's not a parallelogram, since not all opposite sides are parallel. So the way to do that is to determine the slopes, right? If we know that this slope is the same as this slope, then we know that they're parallel lines. And if we know that this slope is the same as this slope, then we know that they're parallel lines. So it's really just a question of using that slope formula. So the first thing I'll do is I'll take a look at the longer lines here, AB and CD. And I'll see if AB and CD are parallel to each other. So first of all, I'll get AB. I'll get the slope of AB, and I'll say A is equal to, and so I'll call this my x1 and I'll call this my x2. So it's going to be 10 minus 4 over 6 minus negative 6. And 10 minus 4 is 6, and 6 minus negative 6 is 12, which is equal to 0.5. So my slope of AB is 0.5. So now I'm going to get the slope of CD and see if it is also 0.5. It certainly looks like it is, but we can't trust the visual representation. So I'll work CD right now, and I'll say, hey, A is equal to. So for CD, I'll call this my P1 and I'll call this my P2. So I'm going to go Y2 minus Y1, negative 4 minus 2, over X2 minus X1, negative 8 minus 4. That becomes negative 6 over negative 12, which is equal to positive 0.5. So this one, A is equal to 0.5. So far, this could be a parallelogram, right? It could be a parallelogram so far because these two line segments are parallel to each other. But that's not enough, right? It's not enough that AB and CD are parallel, although we know that that's true. We also have to see that AD and BC are parallel. In other words, the short edges here also have to be parallel. So I'll do that on the right side over here. And first I'll find AD. So the slope of AD. A is going to equal, I'll call this my P1 and I'll call this my P2. So negative 4 minus 4 over negative 8 minus negative 6. Negative 4 minus 4 is negative 8, and negative 8 minus negative 6 is negative 2. Negative 8 over negative 2 is positive 4. So my slope of AD is A is equal to 4. So now I'm going to check to see if this is also a 4. Let's see. Let's get the slope of BC. So for BC, A is going to be equal to, I'll call this my x1, y1. I'll call this my x2, y2. Again, the order doesn't matter. So I'm going to go 2 minus 10 over 4 minus 6. 2 minus 10 over 4 minus 6. That's negative 8 over negative 2, which is positive 4. So we can now say that CD is a parallelogram since all the opposite sides have the same slope. And we're done. All right, so we're looking at parallel lines. This is question number 3. Are the lines represented by the following two equations parallel or not? And justify your answer. So third question on parallel. So by now we know we're looking here really at slope. And we know that we can't really make any determinations until we have isolated y's. And so I'm going to take 2 seconds and do those divisions on this equation, dividing everything by 2 to isolate that y, and that's going to leave me with y is equal to negative 9x plus 36. And on the second equation, I've got a little bit of extra work to do, so I'm going to add the 288 to both sides, and that's going to leave me with 8y minus 72x is equal to 288, and then I'm going to add 72x to both sides, and that's going to leave me with 8y is equal to 72x. Don't forget your x, and don't forget that you can't add that 72 with the 288 because it's 72x, right? That has to stay distinct, the x term from the constant. And now I'm going to divide everything by 8, and when I do that, you're going to see that I get 9x plus, better check this one, 288 divided by 8, I think gives me 36 as well. So I'm now ready to answer the question, are these lines parallel or are they not parallel? Remember, parallel lines have to have the same A. And you can see that the A over here is a negative 9, whereas the A over here is 9, positive 9. And those numbers are not the same. A 9 and a negative 9 are not the same number. So these lines are not parallel because they have different slopes. And if the slopes are different, the lines will not be parallel. Now, one thing I will point out to you, it's worth mentioning, is what if this had also been a negative 9, right? So what if when I did the calculations, if this was a positive 72 and I had to bring it over and subtract it, if this also became a negative 9, now you'd be tempted to say they were parallel. In fact, they would be parallel, right, if they had the same slope. But remember, there are two types of parallels. And I just want to remind you what's interesting in these equations is they have the same y-intercepts. So if this had been negative 9x plus 36, the same as this, then that would have been two lines that crossed right over each other. They would have been coincident lines. Parallel and coincident because one would overlap the other. They would have been exactly the same equation, and it's worth pointing that out. But because those slopes are different from each other, well, we know right away that those are not parallel lines.